Yeah, so once again, you're welcome to this channel. So in this session, we'll be learning computer systems and how software works. So if you're new to this channel, like the video, share, comment your questions, and subscribe to the channel. So for this section, we are going to be understanding the machine. We're going to be understanding the machine, computer system, and how software works. How software interacts with hardware, operating systems, memory, CPU, storage, and networks. So this will give you a broader knowledge of what happens within the hardware, the relationship, the communication between your software and your hardware. So in the earlier video, we learned about fundamentals of software engineering, the software development lifecycle, and we went through how the front end communicates with the back end. But in this section, we are doing more of that, but in the hardware aspect of it. So we are going to be learning how the software communicates with the actual hardware machine, the RAMs, the memories, the CPUs, and the network devices of your machine. So okay, this will help you as a student to write better software when you understand your machine. So in this session, what we are going to cover: system overview, hardware, OS and software layers, memory hierarchy, registry cache, RAM, virtual memory, the operating system, processes, threads, scheduling, system calls, code to execute, compilers, interpreters, the run pipeline, and then the CPU, fetch, decode, execute, and performance. For the storage, we'll be learning HDD versus SSD, and then we're going to be learning about the file systems. Now for the networking, we're going to be learning how computers communicate in a network, and then concurrency. That's we're going to be learning parallelism and concurrencies. So stay tuned to the end so that you have the adequate knowledge to guide you through your software development journey. So this knowledge is very important because when you are using AI to build, you can be able to design your software properly, like we discussed in the first class. So moving forward, okay, we also have the IO devices, which stands for input and output, and then devices, how input and output actually works. So why this matter? It matters for writing software that respects dimensions. So system overview. What is a computer system? Now this might sound simple, but then we have to get the actual knowledge here. So a computer system is a stack of layers, physical hardware at the bottom, an operating system in the middle, and the application software on the top. So a computer system is a stack of layers. So it's not just the hardware machine. So the computer system has to do with the physical hardware layer, and then the operating system, which stands in between the application softwares. Each layer exists to hide the complexity of the layer below it. It is called abstraction. So the operating system hides the complexity of the hardware, and then the application software hides the complexity of the operating system. And these um, hiding of complexity is called abstraction. So abstraction. So software doesn't talk to the hardware directly, it talks to the operating system, which talks to the hardware. So it's kind of the operating system is the middleman that receives communication from the application software and then transmits those communication to the hardware for proper program execution. Understanding these layers helps you reason about performance, bugs, and system limits, not just write code that happens to work. So when you understand the full functionality of these layers, it helps you to reason about performance, bugs, and system limits. Like we said, when designing a software, you consider scalability, bugs, and improvements. So understanding these layers helps you work on that. So you reason performance, you reason bugs, and then system limits, not just write code that happens to work. So hardware, when we talk about hardware in this context, we're talking about the CPU, memory, storage, and network devices. So now we're talking about operating system. We're talking about the system that manages hardware and runs programs, which you can get an example of an operating system like Windows, the Mac OS, the Linux, the Ubuntu, and the rest of that. Now for the application software, they are programs you write and use. So these are the main applications that you interact with when using a computer. For example, your notepad, your WordPress, your Word documents, and your file explorers. Those are application softwares. So in practice, when your code calls print hello, it doesn't touch the screen directly. It asks the operating system, which asks the display driver, which talks to the graphics driver. So when you run hello world in your code, it doesn't touch the screen. So the hello world doesn't go directly to the screen. But rather, that program that you run, what it does is it asks the operating system, which the operating system asks the display drivers, which the display drivers then talks to the graphics hardware to display what you've run. So if I should open a software, let me say this is my notepad, and I click on it. So the notepad itself doesn't go ahead to pop itself up in the screen. What it does, that action you clicked talks to the operating system, and the operating system talks to the drivers in charge for running that particular program, and then you get your display. The hardware software stack. So application, browser, games, and your code, library and runtime, language runtime, standard libraries, operating system, process management, memory management, file system drivers, hardware. We have the CPU, the RAM, the storage, the network interface. So these are the layers. We have the application layers, the library and the runtime layers, the operating system layers, and then the hardware layer. So it goes this way. You communicate with this one, with the applications. As a user, the application sends your actions to the library and runtime. The library and runtime sends those actions to the operating system, and the operating system communicates directly with the hardware, which is the CPU, the RAM, the storage, and the memory interface. So now we're going to discuss about the CPU. The CPU, the machine's brain, that is, the CPU, the central processing unit, executes instructions. So the only thing it does is fetch, decode, and execute over and over billions of times per second. So what the CPU does is to fetch information, is to fetch commands, decode those commands, that is to understand this better, and then execute the commands or instructions and do that over and over again billions of times per second. So it does these steps: fetch, decode, and execute billions of times per second. So it does it in split of time. So clock speed, GHz, measured how many cycles per second the CPU can perform. So when getting a laptop or a new computer, you happen to check the GHz. Some laptops you see 2.8 GHz. So that is the measurements of how many cycles per second the CPU can perform. So not directly how fast it feels for every task. Modern CPUs have multiple cores, each capable for executing instruction independently, enabling true parallelism. So this will make me explain parallelism. So parallelism is running multiple commands, running multiple execution in parallel. So this execution is running at the same time this other execution is running. So it's more like multitasking at the same time without having to queue the tasks. So modern CPUs that have multiple cores, this make them capable for executing instruction independently. So they run multiple instructions independently. The CPU only understands machine code. That is very, very important to note down. The CPU only understands machine codes, binary instructions specific to its architecture. So you can see some laptops, we have x86, ARM, and etc. So it indicates the kind of machine binary instruction specific to the architecture of that particular computer. So stay with me. I know it's sounding kind of complex to understand, but with time, everything will make sense when we are running down the entire section. So there are the cores, independent execution units. So they are the independent execution units. The clock speed, I've explained the GHz, and then the cache. So what is the cache? The cache is tiny, ultra fast, on chip memory. So it's kind of a very small memory set for immediate program execution. So when the computer is executing your program, it has a memory where it stores immediate information or instruction that it needs to run that particular execution. In practice, a phone's ARM chip and a laptop's x86 chip both run the same Python code, but the interpreter compiles it to different machine code underneath for each architecture. Please stay with me. This is sounding more complex, but stay with me. By the time we are done with this section, you get to understand everything clearly. Now also the CPU. The fetch, decode, execute cycle. This is how it is. So the CPU fetch instruction, then decodes its control unit, interprets what the instruction means. So when you get the instruction, the control unit, that's the CU, interprets what those instruction is, and then the arithmetic logic unit, the ALU, performs the operation. So it executes it and then stores it. Results is written back to a register or a memory. So it stores it. So when the CPU fetch the instruction, decodes, executes, and then store. So in a more simpler diagram, you would see fetch or input, process. These two will be for process, and then output. So it's either storing it or displaying it back to the user. In practice, a 3 GHz CPU runs roughly 3 billion of these cycles per second. Modern CPU use pipelining to overlap fetch, decode, execute of different instructions for extra speed. So I'm not going to be going deeper than this because of, okay. Now the CPU. What actually makes the CPU fast? Now these are the factors that make the CPU fast. This is what it means, and then impact on software. The clock speed, the cycle executed per second. So it helps single-threaded. So higher helps single-threaded sequential code. So it helps single-threaded and sequential code. So the core counts, number of independent execution units, that's the number of cores in the computer, enables true parallel execution across threads. Cache size, fast on-chip memory close to the core. So it's a fast on-chip memory close to the core where immediate information or resources are stored for program execution. So what is the importance on the software? It reduces costly trip to slower main memory. So it reduces costly trips to slower main memory. So it helps a slower main memory reduce costly trips. Instruction sets, ISA, the vocabulary the CPU understand. So x86 and ARM, what it does, it determines binary compatibility across devices. So the binary instruction that this particular computer can understand will be different from another computer's binary instructions. So it depends on the architecture. So some computers have an architecture of x86, ARM, x32, and all that. So pipelining. What is pipelining? Pipelining is overlapping stages of multiple instructions. Improve throughput without raising clock speed. So pipelining improves throughput without raising the clock speed. So in practice, for example, a video game engine becomes more core. A video game engine benefits from more cores, parallel physics/AI rendering thread. A single recursive algorithm benefits more from lock speed and cache. So a game engine benefits from more cores. So it is better to have more cores for a game engine. And then a single recursive algorithm benefits from more lock threads. So if you have a program running a single recursive algorithm, you should lean towards using more lock speed and cache. So you increase this and then your cache size. But then if your program is a game engine or a heavy graphic program, you should lean towards utilizing more cores. Memory hierarchy. The memory hierarchy, speed versus size. So the registers are inside the CPU core. It is about 1 kilobyte or less than. So okay, and it processes in less than 1 nanosecond. So then the next memory is the cache, L1, L2, L3, that's layer 1, layer 2, and layer 3. They are on chip very close to the CPU, so but not inside the CPU. The registers are inside the CPU. They are more tiny memories inside the CPU, but the cache are close to the CPU, ranging in size of about kilobytes to megabytes and processes within 1 to 10 nanoseconds. So now the RAM, which is the main memory, is volatile, fast, off-chip, goes about gigs and processes in about 100 nanoseconds. Now this the disk SSD storage is persistent but far slower and ranges about 1 terabyte to about 10,000 plus nanoseconds for processing. Faster and smaller at the top, slower and larger at the bottom. So these smaller memories are close or inside the CPU. So the register is inside the CPU, the cache is inside the CPU, is close to the CPU, and then the RAM, more volatile, is also inside the CPU, beside the CPU. But then these SSD, I call them external or secondary memories. So in practice, a cache miss that forces a trip to RAM can cost 100x longer than a check hit. So memory hierarchy, RAM and virtual memory. RAM, the random access memory, holds the code. So the code lives in the RAM and data a running program is actively using. So it holds the code and data a running program is actively using. So when you execute your code, those code are transferred immediately to the RAM and all the data that program is using at that moment. So it's volatile, meaning contents vanish on power off. So when power goes off, every information, every data on your RAM goes off. So now each running process gets its own virtually address space. So each running process gets its own virtual address space managed by the operating system. So programs can't accidentally read or corrupt each other's memory. So every program that is running in your computer, the RAM allocates to it virtual address spaces. So it won't be said or it's not possible for programs to accidentally read or corrupt each other's memory. The OS maps virtual addresses to physical RAM addresses using page tables invisible to the running program. So the OS maps virtual addresses using page tables invisible to the running program. When physical RAM is full, the operating system can swap less used pages to disk. So moving forward, storage. Now the HDD versus the SSD. You've heard of HDD and SSD. These are both secondary memories. So how it stores this up. The HDD hard disk drive, the SDD solid state drive. So the HDD is magnetic spinning platters, mechanical arm, and then SSD flash memory chip, no moving parts. So the HDD has spinning platters. Now for speed, the HDD is slower, mechanical seek time. Now the SSD is more faster, no physical movement needed. So when getting a computer, go for a computer that has an SSD. That is much more recommendable. Now for durability, the HDD is vulnerable to physical shock. The SSD is more resistant to physical shock. So the HDD, there is a way you would shake it or it would hit somewhere, it will stop working. But the SSD is much more reliable, cost per gig, cheaper for large capacity, and more expensive per gig. So the SSD is always expensive than the HDD. Of course, the SSD should be because it's more reliable and durable than the HDD. Typical use. The HDD is used for bulk archivable storage, but then the SSD can be used for operating system drives, databases, latency sensitive workloads. So when you want to run a program that is latency sensitive, so you don't want any delays, go for the SSD. How the operating system manages resource. So the operating system, the OS is the software layer that manages hardware on behalf of every running program. So the operating system manages the hardware on behalf of every running program. It decides which process runs on the CPU and how long. That is scheduling. It allocates and protects memory so processes don't interfere with each other. So the operating system is like the middleman, like we said, and it also manages file, devices, network access through a unified set of interface. Without an operating system, every application would need to control hardware directly, so which is impossibly or complex and unsafe. So that is why the operating system serves as the middleman to manage the hardware devices on behalf of every running application in your computer. So it does this by scheduling, that is deciding what runs and when it should run. So the operating system decides what runs and when it should run. Let me use, for example, in your Android phone. So your the Android is the operating system, Android operating system. When you click your TikTok app, and then it is the operating system that decide that this app should run now. But then if there is another app that is running and there is no memory space for the TikTok to run, you find out that the Android device is going to lag. And with that, what is happening at that moment, the operating system is resisting the TikTok from opening up because there is no space, there's no memory allocation for it yet. So it holds up the execution of that TikTok app. That is why you can say your phone is lagging. So the next thing the operating system does is protection, isolating processes from each other. So like I said, when there is no memory address left to allocate to the TikTok app, what the operating system does is to hold up that execution until there is a memory address space to assign to that particular TikTok app. With this, it is processing the TikTok process from interfering with the other running application processes. Now, resource management. The operating system helps for um, file accessibility and device accessibility, memory accessibility, and network accessibility. So basically, when you're running your app, when you're building your app, it's the operating system that gives your app access to files within that particular device, right? and then also makes your software to be able to see other devices connected to your device. Let me use, for example, um, you're on an AirPod and then you want to listen, okay, you're watching a video on TikTok. Now, it is the operating system that routes the sound of your TikTok video to the AirPod. So that is what it does. It manages everything. It's just like the manager of the computer. So when you communicate with your app, the operating system, the app communicates with the operating system, and the operating system works with the computer hardware to execute your program or your request effectively. So now the operating system processes versus threads. So I'm just going to be explaining this real quick. A process is an independent running program with its own memory space, right? So it's an independent memory program with its own memory space. It has its own memory space. Now, the memory type is isolated. It has its own address space. The process has its own address space. The memory are isolated. Now, creation cost is very expensive. Now, the operating system allocates a full new memory address, like I use, for example, the TikTok. Now, when your process is running, when the TikTok process is running, the operating system allocates a full new address space for that particular process to run. Now, for the communication of a process requires explicit IPC, which is pipes, sockets, and shared memories. So it requires explicit IPC. Failure impact. A process can crash typically, but doesn't affect other processes. When your TikTok app crash, it does not affect other apps. Now, for example, when you're on your laptop, let me say you open up Microsoft Word and then you open up Microsoft Excel. At a point, the Microsoft Excel can write not responding. This is common for Windows PCs. So you see the one of the applications you open up will say not responding, right? But then the other application will be responding quite all right. Now what happened is that the second process crashed. So the crashing of the second process did not affect um, the first process. So a crash typically does not affect other process. Now for the thread, a thread is a unit of execution within a process. Sharing its memory is a unit of execution within a process. So threads are units of execution within a process. For example, let me say you are running a process like opening up an app. Now, opening up those apps, there are unit tasks that runs independently that helps that particular app to open up, right? So those unit tasks are threads, right? So for the memory, threads share with other threads in the same process. So um, different threads share memory with other threads within the same process. So um, creation of threads are cheap. It reuses the parent's process resources. So it reuses the the resources of the parent process. So communication, the threads communicates direct via shared variables. So needs synchronization. Now, a crash can take down the entire process. So when a single unit execution fails, the entire process will fail. Yes, the entire process will fail because those unit execution work together successfully to make that process to be executed. So when one fails, it's just like a checklist. For this process to be executed successfully, these unit processes, these threads should execute successfully. So if one fails, so the entire thread fails, and then the process also fails. The kernel and system calls. So this is not for you to understand deeply, but then the kernel is the core of the operating system. Now, it is the only part with direct access to the hardware. Application run in user mode and must request kernel services through system calls. So this is to help you understand what happens within the hood when communicating with a software so that you have a better understanding when you are building your software. So the user mode, your application code runs here, right here in the user mode. It is restricted from the hardware. Now, what happens? The user mode, where your application code runs, sends a system call, like something like read, write, open, fork. So that system calls routes everything to the kernel mode. So the kernel right here directs hardware access. So it communicates with the hardware. It communicates with the CPU memory disk to execute what this user mode have requested through the system call layer. File systems organizing persistent data. Now, a file system is how the operating system organizes raw bytes on a disk into files and directories you can name or navigate. Now, when you open up your file app in your phone or in your laptop, that is your file explorer in your laptop, you find out that those files are arranged in a way that you as a user, you can navigate them, right? So file systems is how the operating system organizes raw bytes on a disk into files and directories you can name and navigate. So with this now you get to understand that those files within the hood in your operating system, they are raw bytes. They are raw bytes. They are not yet full files that you can name or navigate. It is the job of the operating system to arrange those and organize those raw bytes on the disk, which are on the disk, into the files and directories you can name and navigate. So for directories, okay, let's finish with this. So file system tracks which block of disk belongs to which file. So which block of disk belongs to which file and which block are free for reuse. Now, metadata is the name, size, permission, timestamp. So it is stored separately from the actual file contents. When you open up your file explorer, you you right click on the file, you go down to properties, you will see the name, the size, the permission, the timestamp. So the operating system uses the file system to do what? To store this metadata separately from the actual file content. So it stores the metadata. The metadata is basically the name, size, permission, and timestamp of your file. So it stores them separately from the file contents. Now, different file systems are the NTFS, APFS, and the X4, which make different trade-offs in speed, reliability, and features like journaling and crash recovery. So when formatting a USB drive, for example, you get to see some of these file system options. So this helps for accessibility and trade-offs in speed, reliability, and features like journaling. Let me say, for example, not all operating system allows access to some file types. Now, there are some file types that if your file system, that if your USB is set to, you cannot access the contents of that USB drive in a Mac OS. So coming here, dictionaries are hierarchical organization of files. So that is dictionaries, directories, I mean. So that is the directories. Should I say folders rather? That's the way you understand it. Folders. The paths to where your files are stored. So the metadata, like I said, is the name, size, permission, and timestamps. While journaling is a crash safe recovery of changes. So if um, if your system crashed, there is a crash safe recovery that is being um, handled by the file system so that you can recover um, from your crash. So it's more like doing undo, right? It's more like doing undo. Deleting a file usually marks its disks blocks as free rather than erasing the data. This is the reason why most people or most um, computer intellects will tell you that no file is ever deleted from your system, so from your computer, because when you delete a file, it usually marks that particular file. It marks the disk blocks as free rather than erasing the data, which is why deleted files are often recoverable until overwritten. So no matter how you delete a file, it's still recoverable until it is overwritten within the file systems. So for you as a user, you cannot actually tamper with these file systems except you're an expert. That is when you can tamper with it. So your files are not completely erased. The data are not completely erased. Instead, what happens under the hood is that the file system marks the disk blocks of that file as free, so it can be reused by another file. Now, networking. This is the interesting part of it, so just stay with me. Now, how computers communicate in the network. Now, getting data out and then getting it there reliably. So, getting data out, your network interface card, that's your NIC, converts data into electrical stroke radio signals. So data is broken into packets. So before a data is sent from your computer to another computer through a network, it is broken into different packets. Now, each with source and destination addresses. With these source and destination addresses are not usually seen by the user, right? So it is something that happens under the hood so that the network layer can understand where the actual packets or the data is going to. So the data is broken into packets, each packet with source and destination address. So each packet are sent separately. Yeah. So now the routers forward each packet towards its destination hop by hop. So it forwards its package one by one to its destination. So if I should send you a text message, that text message is broken into packets with the destination and then with the source address. Now those packets are then sent individually through that network to you. So when you receive that particular text message, so it comes in packets. It comes in packets, and when it comes in packets into your device, those packets now packets can arrive out of order. Like I said, it arrives individually into to you and then are reassembled at the destination. So when it gets to you, it is when it is reassembled. For example, if you have received a text message, at the first glance it might be empty, and then you receive the the last part of the message before the header of the message will appear. It happens most of the times. So it is what is happening there exactly. So the packets are sent individually to the destination hub by hub, and it can arrive out of order. And when it arrives, it is reassembled in that at the destination, getting it there reliably. So how does this packet get to the destination reliably? So the TCP guarantees this delivery. So this is the TCP guarantees delivery and order. So the TCP transmits lost packets automatically. So any packet that happens to be lost, the TCP transmits it in automatically. Now the UDP skips these guarantees for speed. The UDP protocol is used for video and gaming, and then DNS, that's domain name servers. So it skips these guarantees because it wants to rely on speed. Now there is also a network layer called the IP address, which identifies the machine. Now the ports identify which application on that machine. For example, the IP, when you hear IP is the address of your machine. Every machine using the internet have an IP address. So that IP address is like the house address of your machine, right? Now, the port is like the apartment of the particular application that you are using on that machine. The port is the particular um, apartment number, yes, I would say, of the of each application on your machine. Each application have a specific port they are running on. So now the DNS translates human readable domain names into IP. So when you search youtube.com, that is a DNS. So that youtube.com you search on Google, go through the DNS, the domain name servers, and then the DNS translates that youtube.com into the actual IP address. Note that in the network layer, um, IP addresses are not written in letters. It is only in numbers. It is only in numbers. This is the way that the network layer will understand the location or the address of your machine. So moving forward, code execution. This is the interesting part, from source code to machine code. Now, the approach. Now, there are approaches here: the compiled approach, the interpreted approach, and the JIT compiled approach. So, we are going to take this carefully, so please understand this. Now, for the compiled approach, how it works: the entire program translated to machine code before running. So the entire program is translated into machine code before it is run, before it is being executed, right? So the trade-off here, why this must be like a con, is that it has faster execution but slower iteration. It must recompile, right? So it has faster execution. That is, when the when the program is translated completely to machine code, it runs faster after that, but it becomes slower because it have to compile everything from the beginning. So examples of programming languages that use this compilation approach is the C, the C++, the Rust, and then the Go. The interpreted approach. The source is read and executed line by line at runtime. So your program, your code, whatever the AI tool generates for you, is read and executed line by line at one time. So the trade-off for this is that slower execution but instant iteration, more portable. Examples of programming languages that use this approach is Python, Ruby, PHP. Now, for the Git compiled, um, how it works. It is interpreted first, hot code compiled to machine code during execution. Now, the trade-off is balances startup speed with peak performance. So JavaScript does this now with the V8 engine, and then the Java um, virtual machine. So um, these are the approaches. As a vibe coder or someone who will be using AI to generate a software, a code, um, this is not too necessary for you to grasp right now. But then moving forward, code execution journey. Now, when the AI builds your app for you, when the AI builds your app for you, this is what it looks like. Now, it has the source code, that is the code that makes the actual software for you, right? Human readable text you write, or the AI tool is going to write for you. Now, it compiles or interpreter. It sends the code goes through the compiler or the interpreter to translate that particular code to machine code or bytecode. Now, when it's interpreted or compiled, it is executed. So, executable slash bytecode instruction are ready to run. Now, when those instructions are now executed, now it has remember at this point it is translating or compiling it or interpreting it to um, executable bytecode that the machine can understand, right? So those instructions are ready to run, and when they are executed, the operating system loads them, loads the program into memory as a process. So it is the duty of the operating system to load those program into memory as a process, and then the CPU executes them. So your code gets interpreted, the bytecode or the executables are ready. When they are on, the operating system loads them into the CPU for processing. Now the CPU executes them. So concurrencies versus parallelism. So definition: concurrency is the management of multiple tasks that makes progress over overlapping periods. So um, requires what it requires um, can happen on a single CPU via time slicing. So it can happen on a single CPU core via time slicing. So the goal for concurrency, um, structure and responsiveness. For example, a web server handling and many requests by switching between them. Now, parallelism is executing is definition executing multiple tasks at the exact same instant. Like I said, requires multiple CPU cores or machine. Raw throughput, do more work per second. A video encoder splitting frames across 8 CPU cores. So let's go ahead. Now, inputs, outputs, talking to outside world. Now, the input devices, that's the keyboard, disk, network card, display, are orders of magnitude slower than the CPU. The OS uses interrupts, so the CPU doesn't have to constantly check for whether a device is ready. Device drivers translate generic operating system requests into hardware-specific commands for each device. Well-written software treats input-output as asynchronous where possible, so slow devices don't block the fast CPU work. So a well-written software treats input-output as asynchronous where possible, so that slow devices do not block fast CPU work. Now, for example, the input devices are the keyboard, mouse, network sensors. Output devices are the display, printer, speakers, network, and then network interrupts are device signals, the CPU when ready. Now, bringing everything together. Trace what happens when you run hello world. You type Python hello.word and press enter. The shell, that is a command, reads your keystrokes via the OS. So let us use another example for this one. When you run an application in your device, now a shell reads those that click the keystroke you clicked, and um, yes, so the program reads it through the operating system, which is sent to the CPU for execution. Now the shell asks the OS to create a new process and load the Python interpreter into memory. Now the OS loader maps the interpreter's code and your script into the new process virtual address space. The interpreter reads hello.py, passes it. Let us say this hello.py is maybe your program or your application or your um, software. So the interpreter reads the hello.py, passes it, and begins executing bytecodes instruction. Print hello world triggers a system call requesting the OS write bytes to stand output. So then the kernel forwards those bytes to the terminal driver and renders characters on your screen. Common performance pitfall and their root cause. So app becomes sluggish with many tabs / programs open. Yes, so when you are using your device and then your apps become sluggish when with many tabs and programs open in your phone, the root cause is that the RAM is exhausted, the OS is swapping pages to disk. So the layers that are involved in this is the memories and the virtual memory. Now, another pitfall case is loop over an array is much slower than expected. This is caused by poor data locality causing frequent cache misses. So the CPU cache and then the memory hierarchy is involved. Multi-threaded code and all that. Let us take this last pitfall. App on one machine crashes on another. It is most especially when you are um, using AI to write code. Okay, let us go ahead for this before the last one. Server feels slower under load despite low CPU usage. Now, what causes this is blocking, synchronous input output, stalling request handling. Now, the layers involved is the input and the output layers, that's the IO layers, and then the networking layer. So when your server feels slower under load despite low CPU usage, it is caused by blocking. Now, the CPU is blocking some synchronous IO and stunning request handling, right? So it's either the CPU is blocking some IO or there is a synchronous IO stunning request handling. So um, now when app runs fine on one machine and crashes on another, like I said, you see this more when you are building with AI. Now, what causes it is assumes an instruction set or operating system feature is not present. So it's either an instruction set within that particular application or an operating system feature is not present. Um, the layers involved are the hardware and the OS abstraction. So when testing your software you build with AI, you will come across this particular problem very well, because when you are testing with different devices, you will come across this particular problem. So just know that it's either there are instruction sets that are not present, or um, there is an operating system feature that is not present in that particular device. Now, so with this, we will come to the end of today's class, because this is the last part of it, and then anticipate for the next class. Thank you so much, and if you've gotten to this extent, please endeavor to like and share the video, comment your thoughts, and then your questions, and also subscribe to the channel. So this particular class today is meant for better understanding how your software communicates with your operating system, and how the operating system communicates with the hardware. Thank you very much, and see you soon.